Mr. Strauss is filmed for a live studio audience. Any rebroadcast cannot be done without my express written consent. All right, so this, okay, so that question mark is the atom. We don't know what it is. So we want to know what the atom is, so we send in some sort of way to measure it, or a probe. And what we're going to probe the atom with is light. So I'm going to turn on my light gun. Nothing's happening. Come on, light gun. Oh, I got to hit play. There we go. So it's shooting all different photons of light. Now, if you watch carefully, every once in a while, oh, do you see that?
No.
Piece of light. Well, oh, there's another one that way. Do I gotta slow it down for you?
No, and again.
Oh God.
So every once in a while, a light will hit something and bounce off. So if it's hitting something, there you go. That would mean that there must be something to the atom for it to bounce off. And so we have all these different predictions. And the first one was the billiard ball model, but the atom just must be a solid ball. And if it hits the ball, it bounces off. But that's way too many than what was observed, right? Here there's like tons of them bouncing off. Then we've got good old J.J. Thompson. J.J. Thompson, remember the red stuff is the pudding? The proton is the vanilla pudding there?
Yeah. And
that little blue ball there bouncing back and forth is the electron. And if the right amount of light hits the electron, let's start it over. It's not moving right now. See, the electron's just sitting there. But if the right type of light hits the electron, it will start it to vibrate. And if you get enough light, you'll get that electron to pop out of there. Boop. See, now it's vibrating. Boop. And then we move on to good old-fashioned Rutherford, where the electron goes around the nucleus. But the nucleus has got a positive charge, the electron has a negative charge, so they will be attracted to each other and go kaboom. And we know that atoms don't explode like that. Then we have good old Niels. With Niels, he said the electrons must orbit in quantized levels. And so these circles correspond to the different levels. And if you have enough, if you have the right kind of energy, it will jump to a higher level. So right now it's in the lowest level, level 1. See, it's going to jump. Hey! Now it's in the second energy level. When it falls, it will give off light. See? Oh, give off light, it fell. Let's see if it jumps again. Oh! Jumped out to the 6th energy level. When it falls, it will give off light. Oh, it fell to the 5th. Where did it fall? Oh, all the way to the 1st, gave off light. And again, Bohr could not explain why the energy levels were quantized, but just that they were. Bohr didn't realize that the electron had part wave nature. When you take into account that the electron is more than just a particle, but both a particle and a wave, then we move to the Schrodinger model. So, now look what happened to the electron. There it's a little blue ball circling. And there we're representing the electron as a wave. And you can see it vibrating with an amplitude and a frequency. And the wave can only vibrate at certain allowable wave values, because waves come in whole numbers. N equal to 1, N equal to 2, N equal to 3. So right now, we're at N equal to 1, the first fundamental wave, 1 amplitude. N equals 2, 2 amplitudes. It fell back to the first.
Does this one give off light too?
Yep, so just like the same, right? It will absorb light to jump. When it falls, it will give off light. Where'd it go? Didn't see it. There it is. Fell from the second to the first, it gave off light. And so that's, now it jumped out to N equal to 4. It doesn't have to fall all the way down, nope, but it did. there's the light came off in that direction, photon of light. So that's red light, that's green light, that's ultraviolet light, that's purple light, that's blue light. So right now we're bombarding it with all different types of light. But we could change the light and just do one type of light. I could just do blue light. Isn't that pretty? But blue light doesn't have the right amount of energy to make it jump. I could do red light, but it doesn't have the right amount of energy to make it jump. You need the right kind of light, and I think it's ultraviolet.
Yeah.
Let's try this ultraviolet.
If it's going all the way at the end.
Is it?
No, the other end.
Well, I know it's ultraviolet, but
Keep going.
I'm not getting the right wavelength.
Keep going.
Well, that's the way it goes. Now, if we mathematically graph the wavelength and the angular momentum and the magnetic field and the spin, we can get our orbitals, and there is our 1s. There's our graph of probability. With the right amount of energy, it just jumped to the 2s orbital probability. And it fell and gave off light. There it jumped to a p. That's the graph of a p, a pz. And it fell and gave off light. So right now the electron is existing in a state of probability of where you could most likely find it. Basically what you saw before and what you're seeing now are the same model, just represented differently. There it jumped to a sphere within a sphere within a sphere, that's n equal to 3. It fell.
What causes it to fall?
It wants to get back to its lower energy state, so it's going very quickly. Basically, oh, there's a PZ, 2PZ, and it fell, gave off light, fell back to the 1s.
Does that always fall back to one?
It always falls back. Why does it fall? It wants to get back to the lowest energy state. I wonder. There we go. There's a sphere within a sphere within a sphere within a sphere. That's n equal to 4. It
Inception.
Fell, gave off light. Just a second.
Charles, you see my perfect circle YouTube video?
I did not see that yet. So let's speed this up, just to give you an idea. And the electrons are always jumping and falling very quickly, going into different allowable states. Oh, that was a 3p. I haven't seen those too often. Missed it again. Oh. Oh, that was a P, but a 2P. Oh, that was. Well, I don't think there's any way I'm going to get it. I'm just not fast enough. Okay, so any questions?
How come the spheres are one way and then they're another way? Why are there different directions?
The spheres are all in the same direction. This is.
When's the next concert?
This is a sphere within a sphere. But when you look at the P's are orientated along different axes. But the spheres look the same. Any other questions?